In this lesson, we are going to look at curve properties. What we're going to look at is looking at mins and maxes and then functions that are increasing and decreasing, a lot of which we're going to work with the derivative. So to begin with, just defining what increasing and decreasing means. If a function is increasing, then f of a, so the y value at an x value of a, is less than the y value when for the x value of b. When my a is less than my b. So the x value of a is less than the x value of b. So that's, for instance, here. Right here, my function is increasing because if I look here, let's say this is 2, and I look here, let's say that is 4. This y value is higher than this y value. So this is higher when my x is higher. This is lower when my x is lower. So that's an increasing function, or part of the function. My function is decreasing when the y value at a is bigger than the y value at b when a is still less than b. So over there, I have to go on this side. So let's say we're looking at this point. That's at -4, and I'm going to look at this point. That's at -1. So therefore, -4 is smaller than -1. My height at a is bigger than my height at 1. That is a decreasing function. When that happens, so when I'm looking at this graph, this whole graph is decreasing when x is less than or equal to 0. When it's less than or equal to 0. So that's from here up. That's decreasing. Versus this function is increasing when x is greater than or equal to 0. Now if we look at this situation, what you will notice is this side, this right side here, where it's increasing. Again, we talked about it's increasing because of this situation. So when this is increasing, if you look at your slope, what do you notice about the slope of all of those values? They're positive. Versus if we look at the decreasing, if we look at the slope of all of those, slope of every tangent, that is negative. And then we have this. Tangent at this spot here is neither positive nor negative. We will include that point in both decreasing and increasing, which is why they are both equal to 0. Different books will go through whether they include it or not. We will be including that point when that slope is at 0. So based on the fact that we know that we're looking at our slope with increasing and decreasing, f of x is increasing across the entire function s if and only if the derivative f prime of x is greater than or equal to 0 for all x in the set in S. Whereas f of x is decreasing on S if and only if the derivative, our slope, is less than or equal to 0 for all x in S. There are some specific functions that are continually increasing or continually decreasing. These are two of those cases. So montanicity is when the function is either increasing for all x in the set of real numbers or decreasing for all x in the set of real numbers. So the entire function is either increasing or decreasing. So this one is monotone increasing. So it's just some vocabulary for you. My slope is never negative. And then this one is monotone decreasing. My slope is negative or never positive. And you will hear me not say it's always negative or it's always positive because it could be 0. So typically you'll hear me say it's not the other one. So for each of these 4 graphs, I want to know what the intervals are, where my function is increasing and where my function is decreasing. So to begin with, you need to figure out where do you have those slopes that are positive. So if you start drawing tangents, I know all those are positive. Okay? And then I also have that 0. So therefore it is increasing from 0 to infinity. Remember, don't include infinity. But it is decreasing from negative infinity to 0. And again, you include 0 on both ends of it. In the second one, you start drawing. So those are positive tangents. So therefore, this is increasing from negative infinity to 0. But then it starts decreasing from 0 to infinity. So pause this for a moment and try to do the second one or the third one and the fourth one and see if you can come up with those. So for the third one, we have a 0, but all of our slopes are all positive. Therefore, it is increasing from negative infinity to infinity because it never decreases along the way. It never gets that negative slope. Here, I'm going to do this in 2 different colors. We have increasing until we have 0. And then we have 0, and we're increasing over here. So therefore, we are increasing from negative infinity to negative 1. Include that negative 1. Union, we start again at 1, and we keep going to infinity. But we are decreasing between there. So therefore, we are just decreasing from negative 1 to 1. Again, make sure you include those points where your slope is 0. So in this 4th degree polynomial, we want to find the intervals where the function is increasing or decreasing. Since we're looking at it increasing and decreasing, we need to know where our slopes are positive, negative, and 0. So if we need to figure out where our slopes are positive, negative, and 0, we have to find the derivative. So the derivative of a 4th degree polynomial, this is a pretty straightforward derivative to take. So 12x cubed minus 24x squared. So if I need to figure out where my values are positive, where they're 0, and where they're negative, because again, this is the slope, what I'm going to come up with is I'm going to create a sign diagram. That sign diagram tells me the negativities that I have. I know where my zeros are, and then I'll figure out is it positive or is it negative. So in order to figure out my sign diagram, I have to find the zeros of my function. So if I need the zeros of my function, I set my slope equal to 0, and I'm going to factor. And what this does is it tells you where you have those zeros, and then from those zeros, you can then plug those numbers in to figure out is it positive or is it negative, and then it's telling you your increasing and decreasing situations. So my zeros occur when x is 0 and when x is positive 2. So on my sign diagram, I put on there 0 and 2. So those are going to be the places where my negativity may change. And that's where I'm going to have to then plug in to check to see what happens. So into my function here, into this, I'm going to plug in a number that's less than 0, that's between 0 and 2, and that's bigger than 2. It's typically easier to put it into the factored form because then you can just look at positives and negatives. So if I put a negative 1 in, this is positive, and if I put a negative 1 into the x minus 2, that's negative. So that's going to be negative. If I put a value between 0 and 2 in, like 1, if I put in 1, this is positive. If I put in 1 here, it's negative. So this is negative as well. And then lastly, I'm going to pick a number that's bigger than 2, like 3. If I put in 3, this is positive, and this is positive, and a positive times a positive is a positive. So what I've just figured out now is where are my slopes negative, and where are they positive, and then of course I had the zeros. So if it's negative, if my slopes are negative, we know that's decreasing. So I have a decreasing function from negative infinity to 2. But I have an increasing function from 2 to infinity. please keep in mind that in order for this to happen, f of x must be defined for all x's on the interval when classifying as increasing or decreasing. You have to be careful of vertical asymptotes and removable discontinuities. We have to exclude those values when we're doing our increasing and decreasing. So it might not be able to be this 2. This might have to be a parenthesis if it's excluding it, and then that would be a parenthesis. So maybe there's a removable discontinuity at 2 or a vertical asymptote at 2, something like that. So that's where our sign diagrams and labeling things correctly is going to be important so that you can see where are there discontinuities, because you cannot include them in your increasing and decreasing function. It is very possible that you will end up having to do, you'll have to do unions with those. Okay, so here's a function where you can see you have a denominator. Since you have a denominator, we're going to have some undefined terms. So to begin with, it just says, show that the derivative is that, and then draw its sign diagram. So to begin with, we need to take the derivative of f of x. You all should know how to do the quotient rule. You should realize that that's a quotient rule. So feel free to pause this and try this on your own, just to give yourself that practice that you can do the quotient rule. But I'm going to also walk through it if you completely forgot. But give it a shot on your own. So to find the derivative, f prime of x, so I'm going to have to find the derivative of both the numerator and the denominator. So I know that it is the derivative of the numerator, 2, times the denominator, minus the derivative of the denominator times the numerator, all over the denominator squared. And you're going to have to simplify this. You cannot leave this as it sits. It did tell us what it should simplify down to, which can help you with that. But we're using this for more things. We're using this to find our 0 values. We have to combine our like pieces together. So it's going to take you some time. So distributing that 2. And then I'm going to multiply 2x plus 2 and 2x minus 3, and then also send through that subtraction. So that ends up being minus 4x squared plus 2x plus 6. And then that is all over. And then this is a quadratic. I can factor that. And then it's squared. So this is x plus 3 times x minus 1. That's the x squared plus 2x minus 3. And then that whole thing is squared. So therefore, both of those terms end up being squared. So again, simplifying out that numerator a little bit, combining all your like terms together, you get negative 2x squared plus 6x. Oh, up top here I missed. This is a minus 6. Sorry about that. And then those 6's cancel out. Good. And then that's over x plus 3 squared times x minus 1 squared. Factor in that numerator, you get negative 2x times x minus 3. And in the denominator, you get x plus 3 squared times x minus 1 squared, which is what they wanted in the top. That's what they showed. So that you just showed the derivative and where it is. So the second part to A that they wanted you to do is to find, or to do your sign diagram. So in my sign diagram, we always list our zeros and then our discontinuities. So when I look at my zeros, what makes this fraction 0? And the numerator is 0. So therefore, I have zeros at positive, well, at 0, and at positive 3. So I have zeros at those two spots. And then I have discontinuities where my denominator equals 0. So I have a discontinuity at negative 3, and I have a discontinuity at positive 1. So at negative 3, there is a vertical asymptote because it does not simplify out in the top and bottom. If it simplified out in the top and the bottom, that would be removable discontinuity. That's your whole. And at positive 1, I also have a vertical asymptote. So I'm going to be looking at those sign changes. I'm going to be looking at the negativities because from each of these values, because this is where I can have those sign changes. It can go from 0 to positive to negative, etc. So now I'm going to start plugging in those values into this equation here where it's simplified to figure out if it's negative or positive. So if I put in a negative 4, so value smaller than negative 3, negative 4 times this, that ends up being positive. Negative 4 in here, that makes it negative a negative 4 in here is going to be positive, and a negative 4 in here is going to be positive. So a positive times a negative over a positive times a positive is a negative. And you're going to do that for all of those. And when you check all those values for everything in between, when I pick a number between negative 3 and 0, it's negative. Between 0 and 1, it's positive. Between 1 and 3, it's positive. And greater than 3 is negative. So now I have my sign diagram. Part B says, then find the intervals where my original function is increasing or decreasing. Again, my original function is increasing and decreasing when my slopes are positive, increasing, negative, decreasing. 0 is switching possibly between the two. So therefore, all of my negative values, it is decreasing. It starts at negative infinity. It cannot include negative 3, even though it has a negative lower than negative 3 and a negative between negative 3 and 0. I have to stop at negative 3 because there is a discontinuity there, and I cannot include negative 3. It is not defined in my function. Union, it is also decreasing from negative 3 to 0. Union, it is also decreasing from 3. It does include 3, though, and it includes 0. Sorry about that. Let's fix those. And it is also decreasing from 3 to infinity. So again, check those parentheses versus square brackets. If it's undefined, it has to be a parenthesis. It cannot include it. So this is decreasing. It is increasing from 0 to 3, but it doesn't include 1. Therefore, it is increasing, including 0, to 1, excluding 1. And then starting back at 1, but excluding 1, to 3. So again, based on your sign diagram, being able to figure out where it's increasing and decreasing, just take note of when it excludes the value. And based on all of this, when we're looking at these derivatives of increasing and decreasing, what we can find are these things called stationary points. And that's part of what's creating those sign diagrams for us. A stationary point is when our derivative is 0. It is going to be a local min, it'll be a local max, or it'll be an inflection, which you'll see. So our stationary points, again, occur when our derivative is 0, which means our slope is 0. They will be a local max, a local min, a horizontal inflection. It could also be an absolute min or an absolute max. If you remember back from Algebra 2 when we were graphing rational functions, we could figure out where across my x-axis we knew our end behavior, but we didn't always know where those turns were along the way, like how high up they went. And I said, just wait, we'll learn that in calculus. That's what we're going to do now. We're going to be able to figure out where those local mins and local maxes are located based on the change of my slope. So there is a local max when I go from a positive slope to a negative slope. Think about this. A positive slope goes like this. A negative slope goes like this. So where those two stop, my slope is 0. It's technically more curved like that. But that's where a local max is, when it changes from a positive slope to a negative slope. There is a local min when I go from a negative slope to a positive slope. Again, at some point it turns, and that's going to be a 0 value. So that's where you're going to have a local min, when it goes from a negative slope to a positive slope. There is a horizontal inflection when it goes from a positive slope to a positive slope, but having a 0 along the way. Or a negative slope to a negative slope with a 0. I'm going to go over on this side. So this has a positive slope, positive slope. It flattens out, and then it goes like this. So that's that cubic. We used that locator point when we were doing cubics. There's that horizontal piece there, and then my slopes keep going from there on each direction. So if my derivative is 0, there's either a local min, a local max, or a horizontal inflection. So what we can do is we can figure out, based on those derivative changes, what the graph will look like without even having to graph all of the key points, without needing your graphing calculator. So in this problem, we just want to find all stationary points. We're not going to do anything more with it. We'll start graphing in the next lesson. So if I want to find all stationary points, what I need to do is I need to figure out where does my derivative equal 0. And then once I figure out where my derivative equals 0, I'll be able to tell if it's a local min, if it's a local max, or if it's a stationary point, or if it's a horizontal inflection. So derivatives, 3x squared minus 6x minus 9. So factoring this, so again, I'm figuring out where does this equal 0, because I need to figure out where those changes occur. So therefore, on my sign diagram, my zeros occur at -1 and at +3. So when I plug values in that are lower, in the middle, and higher, I can figure out whether it's positive or negative, and then we can look at maxes, mins, and horizontal inflections. So if I put a number in down here, so like -2, if I put -2 in, this is negative, and a negative times a negative is a positive. Okay, then I'm going to plug a number in between -1 and 3, such as 0. If I put 0 into the first one, this is negative. If I put 0 into the second one, this is positive. A negative times a positive is a negative. And then lastly, if I put a value in like 4, this is positive, and a positive times a positive is a positive. So just by looking at my sign diagram, I know this cubic function has one local min and one local max. You know cubics look something like this. Okay, and you know that it has a local minimum and a local maximum. So if it goes from positive to negative, so positive slope, negative slope, that means at -1, there's a local max. At -1 something. And then, since I go from a negative slope to a positive slope, that is a local min, and I have a local minimum value, 1x is 3. Well, I still need to figure out what the coordinate point is. So it says find and classify all stationary points, not just find the x values of them. So since I need to find my coordinate points, I know that my slope changes. It's that horizontal asymptote, it's that horizontal tangent. 1x is -1. So if I want the y value, I've got to take my -1 and plug it in here. I need to find f of -1. Again, I'm trying to find the coordinate point in my original function. The derivative just tells me slope. The derivative helps me find where do my slopes positive, negative, and 0. If I want my physical coordinate point, I have to go back into my f of x function. So when I plug -1 back into my f of x function, I get 10 out. Therefore, my y value is 10. And if I want that minimum value, I'm going to take that 3. I've got to put it in there. And when I find f of 3, I get -2 out, -22 out. So therefore, I know what those coordinate points are for my local min and my local max. Again, this is a cubic. You have an idea of the shape of a cubic. The last one, I want to find the greatest and the least value. So we talked about local mins and local maxes. That's where those turning points occur along the way. But there's also those ends. A cubic goes like this, of some sort. So I have this highest point and this lowest point, but then I'm restricting my function, and I'm just looking between those values. So maybe all that does is makes me look at this part of my graph. Well, then I know I have a lowest point here and I have a highest point here, even though local max is here. But if I restrict that domain down, my max value, the highest point, could either be at a local max or it could be at its endpoint. And if I'm looking for the lowest point, it could either be at the local min or at an endpoint. So we're going to have to test all of those values. We'll have to figure out where do I have local mins and local maxes. So I'm going to have to do the derivative. And I also have to plug in the value of -2 and +5 to figure out which of those values are possibly the lowest and highest. So we're going to start with the derivative. We'll just call it y prime. So that's 3x squared minus 12x. Okay. So then I'm going to factor out a 3x, and I'm left with x minus 4. So figuring out where those zeros occur at, I have a 0 value when x equals 0, and I have a 0 value when x equals 4. Sign diagram. based on the sign diagram, plugging in the numbers to see positives and negatives to figure out which is my local min, which is my local max. Realistically, I can just plug in these values. I can plug in 0 to my original function, get my output value, but it does give you at least an idea of which one's my highest, which is my lowest. So I'm just going to finish up my sign diagram really quick. Positive when I put in a number less than 0, negative when it's between 0 and 4, and positive when it's 4 and over. So therefore, positive slope, negative slope, this is a local max. And then negative slope, positive slope, this is going to be a local min. So I need to figure out what my f of 0 value is, what my f of 4 value is, figuring out what those y values are, again, to find the greatest and least value. And then I also have to find the endpoints, -2 and 5. Now, one of the things that is nice is if either of these two x values were outside of my domain, I wouldn't have to check them because it's not within that defined domain. So when I plug 0 in for -2 and 5, I get the following out. So 0 is 5. Again, I'm putting them into this original function. 0 is 5, 4 is -27, -2 is -27, and 5 is -20. So what I end up having is my least values. There's two of them. It's possible that that happens. So my least values occur at -2, -27, and at 4, -27. My greatest occur at 0 and 5. So again, I can figure that out just based on finding where my slopes change. So I know those are relative mins and maxes. And then I also have to plug in the endpoints of it because it does keep going forever to positive infinity and negative infinity. So since we changed how it was defined, we just plug those values in. So again, right now we're looking at finding local mins, local maxes, and then also finding increasing and decreasing. Next, we'll then start graphing these functions based on this information.